Let's start. I will try to finish as fast as I can, just to leave a few minutes for discussion if possible. So I'm Xiaodong Ming. I'm currently a postdoctoral researcher at Loughborough University. I'm working on two projects. One project is about to analyze the impact of extreme rainfall caused by climate change across cities in the UK. The other one is about the integrated flood risk assessment for socio-ecological systems in delta regions in South and Southeast Asia. And my topic today is the high-resolution hydrodynamic modeling for flood forecasting in cities, comparative studies in China and UK. And I'm the presenter, but this work also is contributed by some of my colleagues, Professor Chuhua Liang, Dr. Xilin Xia, and Dr. Jiaheng Zhao from Loughborough University, and Dr. Yun Xing from Nanjing University of Information Science and Technology, and Dr. Ning Ning from Zhengzhou University. And the outline of my presentation will consist of five parts. First one, just a brief introduction about background, then to introduce the urban flood modeling system supported by a high-performance hydrodynamic model, and then show two case studies. One is a case study in the UK, in Newcastle. The other one is the latest flood in Zhengzhou, and then a few conclusions. So beginning the background, I think there's two main backgrounds, two problems. One is climate change, which is a hot topic currently because of the ongoing COP26 conference in Glasgow in the UK. So climate change has brought much more extreme events, both in terms of intensity and the frequency, especially for rainfall across the world. And the other problem is the rapid urbanization still happening in developing countries. So these two problems combined together increase flood risk significantly, and will increase in the future as well. So we have with this series of floods this year in July, only that month, across Europe to China, and killed a lot of people, not only in like developing countries in China, but also in developed world in Europe, which is kind of some unprecedented in many generations. And because of this problem, we think that about the topic of the conference in general, we need to build a resilient city, and flood forecasting is a very important tool to reach that goal. And considering the future climate, there will be more extreme events, and we may need more models, flood models that are more physically based rather than based on experimental parameters calibrated based on the past events. So that's the general idea of this research. So based on this idea, we develop an urban flood forecast modeling system to support urban flood forecasting. And the modeling system, the core of the modeling system is based on a hydrodynamic model. It's called HYPIM. The model consists of three main parts: infiltration, drainage, and the surface flow model. And the model, they take two types of water inputs, the precipitation as rainfall source over the whole domain, and the flow and depth predictions or observations as boundary conditions. We need to consider the upstream flow or the downstream surge or tidal height as influence factors of urban flooding. And the model, we rely on high resolution and high quality DEM data to reflect topography in urban region. And sometimes you also need to consider, actually most times you need to consider human intervention in flood modeling about the reflect of intervention on DEM and also in sometimes drainage networks. And two other important factors when you consider is infiltration and drainage. That in some cases can have strong influence on the final results of flood simulation. And if we have data, we definitely can use the current model. So we don't have data, we can use non-cover data or non-used data to estimate those parameters. So about the model, the hydrodynamic model, HyPIMS, this model is yeah, we already have some presentations about hydrodynamic modeling already, and it's kind of broader scale. This, but usually hydrodynamic model is for small scale because the model usually is physically based, and the HyPIMS is a fully physically based model, and the governing equations is full version of the 2D shallow water equations without any simplification. So those equations, it's just like two key variables in those equations to reflect the status in each time steps. Flow, one is the water depth, the other one is water velocity. And we need to estimate or calculate water depth and water velocity in each time step across the whole domain in each cell. And there are like four key features of the model HyPIMS. Apart from the physically based, the model uses state-of-the-art numerical schemes. It's a finite volume method, Golov type scheme, to reflect to capture the shocking waves during the high dynamic flooding process caused by extreme events. And a very key important key feature is the parallel computing. This can bring the application of hydrodynamic modeling in small case or in a coarse resolution to a large scale high resolution application. Because the CPU traditional way to do modeling the CPU can only consist of few cores. GPU consists of maybe hundreds or thousands of cores, which is extremely suitable for parallel computing in a large amount of cells, which is the typical calculation process in a hydrodynamic model. And another feature is the improved numerical methods. This improved numerical methods can improve the performance of model in some extreme scenarios, like shallow water, extreme shallow water in a steep slope, which is a typical circumstance in cities. This can promote the model, the stability, also to increase speed. So the model is to solve problems in simulating flooding over complex urban topography in a large domain with high resolution, and for extreme events. Some events are even unprecedented, because that's a physical, which means this physical process very important. So to set up the model, we need data, DEM data. That's just an example. We can use LiDAR data, usually have very high resolution, or use some, in the UK, you can use OSD DTM data, 5-meter resolution, then cover data for some parameters to estimate parameters, and crowdsource photos to calibrate model. And you definitely need rainfall input. It can either from radar rainfall forecast or nowcasting, or from numeric weather predictions. And the parameters, as I mentioned, infiltration and drainage. If we don't have data, the suggestion in the UK from the Environment Agency is a 30% reduction to rainfall, and for the drainage is a fixed value of 12 millimeter per hour reduction to rainfall. But this way is kind of problematic, because in some circumstances, when we don't have rainfall, we may still have infiltration and drainage in a short time, because they remain surface water in some cells. So we need to try some other approaches for infiltration and drainage, like to estimate them based on different non-cover types. So the model, the modeling system is applied firstly in a few cities in the UK. So this is just one case in Newcastle. It's to simulate the flood happened in 2012. It's called Toon Flood. The whole domain, the computing domain, is 400 square kilometers, covering not only Newcastle city center, but also a few districts, urban or suburban districts surrounding Newcastle. And the resolution is 2 meters, which means the whole domain has 100 million cells, computing cells. And the speed to finish. Speed is very important if we want to do flood forecasting. The speed is 2 hours runtime for the 6-hour event based on 4 P100 NVIDIA GPUs. Before we run simulations, we need to do some edits about the DEM, because DEM usually still have features about some blocks like overhead bridges or buildings on float paths like rivers or roads. We need to remove those blocks. And the event, Toon flood, is actually not very extreme in the view of many Chinese people if you consider the scale of rainfall events in China. But it's still a very serious event happened in Newcastle, which doesn't have a very high rainfall usually. And so the cumulative rainfall is not very high, 30 meters across the domain averagely. But the maximum rainfall reached over 200 millimeters per hour. And if you look at the bottom right figure, you can find some in some cells there are some rainfall rate even over 300 millimeters per hour. So it's very extreme for a short time. And we use some crowdsourced photos to produce flood extent, inundated extent across the city. Both dry events, dry extent and the wet extent. This for model calibration. And the process, the physical process in each time state can be produced, and we can show the water depth and water velocity in each cell or across the whole domain. This is just part of the city center. We can see the change of the flood inundation. And to calibrate the model, to assess the performance of model, we use the flood extent, as I said, derived from crowdsourced photos, and with some measurements like heat rates, false alarm rates, and critical success index to compare them with the simulated results with the observed results. So its performance is quite good in Newcastle. We can reach around 0.7 critical success index. And this is based on the infiltration and drainage parameters with those values. And we also use the EA suggested results are not that good. So which means the parameters estimation is important, and the result is based on this way. It's kind of more persuading. So we realize the result in Google Earth, so it can be realized in some other OpenStreetMaps as well. And then compare the results with the observed values, observed photos taken by pedestrians during the event. So it can match quite well. Just two examples. This one is in the city center of Newcastle. This one is in the main road outside the Newcastle City Center. And another case in Zhengzhou recently happened, and the domain area is we choose domain area in covering city center of Zhengzhou, not the adjacent suburban region, so only city center. Is 953 square kilometer. The resolution was 5 meters, and the number of cells is 38 million. The duration, we simulate the duration of 16 hours in that day, July 21st. And the runtime was 2.5 hours. This is based on 8 P100 GPUs. So we can see that the extreme rainfall is even much more extremer than the rainfall happened in Newcastle. And we also did some improvement about data, because the data quality, the DM data is not as good as the LiDAR data we use in UK. We got 5 meter DM data from satellite images and improved because the raw data does not really reflect the urban buildings quite well. So we did some edit on the DEM to add the buildings and dig sea, that also reflect the rivers and lakes. And we collect data. This work mainly done by our colleagues from Zhengzhou University to collect flood depths and extend observations by three different ways: survey data, remote sensing data, and crowdsourced data. And this is a results, simulated results compared with radar rainfall. Sorry, I didn't mention the rainfall input is from radar rainfall. It's actually observed rainfall, but we have they can produce like 1 hour nowcasting based on the current circumstances of radar. So the simulated results are compared with observed flood depths at over 700 hotspots derived from the crowdsourced data. The performance goals, we compare the hit rate can reach around 80% to predict whether a cell is flooded or not, or to predict the range of the range of the depths around 70%. So a few conclusions. Firstly, from our experience of these few cases, when we consider urban flood modeling and forecasting, the first key factor is the rainfall forecasting or nowcasting data. We need high quality of rainfall forecasting or nowcasting, and the lead time is important, the quantity is important, and the location, like the center of the rainfall, or is like biased to another direction. Those factors are quite important. There's the quality of the rainfall predictions. And second key factor is the DEM data, because the model is fully predictive based. The DEM data is a key factor, can influence the flow directions and the speed of flow as well. So we need high resolution DEM data for good hydrodynamic modeling in urban region. And the flood observation data is also critical for calibration the model, and more importantly, the estimation of the drainage infiltration, because this factor can be divided to two circumstances. One is when we deal with extreme events, maybe drainage or infiltration are not that important. For example, in Zhengzhou, we found drainage or infiltration doesn't really sensitive. As a result, doesn't sensitive to drainage infiltration because they already have some intense rainfall before that day, and the event is too extreme, which means the drainage capacity just like totally full and can be ignored. It's doesn't matter anymore. And but for less extreme events, like events in Newcastle, we still need to consider drainage and infiltration to estimate them reasonably. And human intervention is also a very important part. We have like topics about presentations about spongy city and some other human interventions on during events like pump stations. So this and also need to consider in the urban flood simulation. And hopefully I didn't take too much time. That's all for my presentation.